Energy issues seem to challenge us more and more each day. Refining in particular plays a critical role in supply and demand issues and remains a vital component of our energy infrastructure. You're here today because you either work for an energy or energy-related organization, or you're simply fascinated with the subject of petroleum refining. For 30 years after the discovery of crude oil, refining consisted of separating these various products by batch processing, a tedious process by all accounts, that involved heating and vaporizing one tank of oil at a time, and a condenser that returned the vapors to a liquid state. Fractional distillation, using the trade columns now used worldwide, didn't come into play until the 1920s. Fractional distillation had been used for nearly a decade to distill alcohols. Yes, the same kind you might enjoy with a cocktail olive or a twist of lemon. Shortly after the Prohibition Act of 1920, many of the technologists from the spirits industry found themselves suddenly out of work. By bringing their distilling expertise to the refining industry, the efficiency of separating crude oil increased by 25%. The 5 basic processes of refining remain the same. They include separation, cracking, reshaping, combining, and treating. Let's have a look at each. Separation, mostly by distillation. Here the molecules remain intact and no chemistry takes place. This is the only process of the 5 that has no chemistry associated with it. Almost every oil reservoir has some gas dissolved in the oil, sometimes substantial amounts. Conversely, almost every gas reservoir has some oil dissolved in it. Sometimes a well can tap an oil formation that is topped by a gas cap, like that at Prudhoe Bay in Alaska. Let's take a look at an oil reservoir. As an oil stream comes up out of the reservoir and out through the wellhead, the pressure drops. The oil and previously dissolved gas mixture goes into a vessel right at the well site called a field separator. As the gas and liquid enter the larger space, the beer bottle effect occurs. The pressure drops further, and the light gases that were dissolved in the crude oil vaporize and bubble out, just like the fizz in a beer when you pop the top. Natural gas is drawn off the top of the separator and the crude oil out the side. Almost every reservoir has water vapor entrained in the oil and gas. To further specify the character of crude oil, refiners have found it useful to lump certain compounds into groups called fractions. Fractions, or cuts, are the generic names for all compounds that boil between 2 given temperatures, or cut points. What you see here is a distillation curve and its fractions. Although the inner workings of distilling columns vary, we'll use the simplest design here to describe how the process works. Distilling columns work on basic principles: gravity and temperature. Inside the distilling column are perforated trays, maybe 100 or so, that sit 1 or 2 feet apart. The perforations in these trays allow the crude oil vapors to rise through the column and the crude oil liquids to fall. Both toluene and xylene are high-octane gasoline blending components. As with ethylene, the double bonds make the benzene ring very chemically reactive. That makes the BTXs, benzene, toluene, and xylene, very popular building blocks in the chemical industry. The reactivity of the double bonds on the aromatics ring can be best illustrated by the numerous petrochemicals derived from them, such as polystyrene, epoxy, and polyesters like polyethylene terephthalate, the water bottle material. The history of cat reforming can best be described as tortuous, but it's important to learn the ups and downs of its evolution in order to understand the dilemmas that refiners face today. Refiners created cat reformers as a method of raising both the volume and the quality of gasoline. If you'll recall from our first lesson, the demand for gasoline grew at twice the rate of fuel oils in the first half of the 20th century. If thermal cracking is like throwing a hamburger on a hot grill for a few minutes, delayed coking is like Texas barbecue, slow cooked all the way through. As we've discussed, coking up furnace tubes is a mess because they are so difficult to clean out. But over the years, refiners, as they gained more knowledge about thermal cracking, found that they could raise heavy feedstocks to high temperatures without coking up their furnace tubes if they used high velocities in the tubes to postpone the formation of coke. That gave rise to the term delayed coking. Let's take a look at the process. The feed to a coker, flasher bottoms, or sometimes cat-cracked heavy cycle oil, is quickly heated in a furnace to about 1,000 degrees Fahrenheit and then charged to the bottom of a coke drum you see here. The heated residue sits in the coke drum and just cooks. So now you know what octane numbers measure. But why are they important? Because the design of an engine demands that the fuel behave in a certain way. The compression ratio of an engine determines the amount of power it can deliver. The higher the compression ratio, the more gasoline can be burned, and together with the longer power stroke, the more powerful the engine.